before I touch this, something important now. Should E equals lambda. When you say this, you say lambda is an upper bound and it is the smallest upper bound. No? And so let's write should E equals lambda. I write if and only if I double it. Lambda is an upper bound, Roman 1. Lambda is an upper bound. Roman 2. Lambda is the smallest upper bound. So this is the meaning of should equals lambda. Again we can say if and only if Roman 1 lambda is an upper bound. Two lambda is the smallest upper bound means any number less than lambda is not an upper bound. Again, if and only if lambda is an upper bound, any number less than lambda can be written as lambda minus epsilon. No? What is epsilon greater than 0? Lambda minus epsilon is not an upper bound. Yes, if and only if lambda is an upper bound of E for each x belongs to E x less than or equal to lambda. So for epsilon greater than 0, lambda minus epsilon is not an upper bound means what? Is not that is bound of E, upper bound of E. What does it mean? Lambda minus epsilon is not an upper bound of E means
less than or equal more. When x is less than or equal to lambda, no, it will be on 4.
there exists some x epsilon belongs to E such that lambda minus epsilon is strictly less than x epsilon. So this is like the working definition. When you prove a should be equals lambda, so you say these things. First you prove for each x belongs to E, x less than or equal to lambda. Therefore, at epsilon, you prove there is an epsilon, x epsilon belongs to E, such that lambda minus epsilon less than x epsilon. So this is like the working definition. Actually, this is how I teach. Because, I mean, this kind of statements, though they are correct, I mean, it's difficult for you to decide how to prove it. This is crystal clear. You have to prove, no matter which x you choose from E, x must be less than or equal to lambda. No matter which epsilon you choose, you have to produce an x epsilon belongs to E, such that x epsilon is strictly greater than lambda minus epsilon. So for inf also the same way. I mean, in his case, sometimes he has epsilon in the book, sometimes he does not have epsilon at all. Epsilon is steady, epsilon continually, epsilon something. But when you look at the lim sup is something to do with the epsilon. In his proofs, no epsilon whatsoever. So it makes the, I guess, I shouldn't say, I have to use the word I guess, it makes it kind of difficult for a student. This way it is crystal clear what to do and how to prove. This is, I don't have my books here. I mean, this is how I teach. This is how I teach, and this is how the students prove that sup of a set is equal to lambda. That's how we do it. For inf, the same way. For inf E equals mu, you can inf E equals mu if and only if for each say x belongs to E, x greater than or equal to mu. I go like, I write it 4 times in front of the students, but now you can do that now. And the second one is for x epsilon greater than 0. Here it is x epsilon belongs to E. Such that x epsilon is strictly less than mu plus epsilon. That's the greatest lower bound. And you have right mu is lower bound of E like that. You need to develop this through lines. If you take any number greater, I mean that's how he says. He says mu is a lower bound. Any number greater than mu is not a lower bound. But to a student, there must be a way to work. So in analysis, you always work with epsilon. Because epsilon can be 10 to the minus million. That's small, but it is still possible. Right? This is far more clear, and the thing is that if you want to prove this, and if you want to prove that sup E is not equal to lambda, once again. Then you can say here this one and this one actually. Here, commas. Oh, and apart. Let's say and. And it should be not equal to lambda. If and only if two things, no? One. Oh. Not one. Oh, not two, no? P and Q, negation of P and Q is not P. Oh, not Q. Not P is direct is X belongs to it. Such that X strictly less than lambda. Oh, direct is epsilon greater than 0. Such that yes, is for each epsilon greater than 0, direct is epsilon, x epsilon belongs to such that x epsilon greater than lambda minus epsilon, here should be then direct is epsilon greater than 0 such that for each x belongs to it. When you go like this, I don't know, I think it's easy for a student for each x belongs to it. The other way around, no? Lambda minus epsilon greater than or equal to x. No? So always this is not actually an analysis book according to me. Yes.
So that should be not equal to lambda. So P is not equal to lambda.
Yeah, of course. It's very good to point this out. Always, if you are talking about, say, handsome boys, to understand the meaning of handsome boys, you have to know boys who are not handsome, at least one of them. Like that, in order to understand sup E, you have to understand not sup equals lambda. In order to understand the meaning of that, you need to understand the meaning of sup E is not lambda. That's very important in mathematics. Then you will understand it better actually. Otherwise, sometimes it may be like by just saying things for the sake of saying. Some people say Sri Lanka is the best country in the world. I mean, you can say when you are going to another country, sometimes at the very beginning you may get the feeling that this is the worst country in the world. Yeah, this is. So, always in analysis it's very important to, it's arbitrarily close, arbitrarily large. These words are, of course, meaningful, but you have to put in, you have to be able to quantify them. You use epsilon for all of them, epsilon, delta, etc. Okay, so here now where are we at? I guess I was definition 6.2.6, we came that far, no? Yes?
No, please have to discuss on that one.
Did we cover definition 6.2.2? Anyway, extended real number system means you add plus infinity and minus infinity to R. Extended real number, you denote it by R star. R star is kind of, R star is R union minus infinity plus infinity. This is R star. So I guess I haven't said and you are not told what is minus infinity, what is plus infinity. We think that you know it, I know it. I mean, that's what he also does. He thinks you know it, I know it. It is that way. By the way, in his, if you think about his definition of real numbers, I guess that's, you have to think about it. Rather than going to so many, taking so many courses. In order to learn, become a mathematician, you have to try to be exceptionally good in one area, say in analysis or node theory. If you are trying to learn, of course, if you are very smart, then these are redundant. Otherwise, if you are a normal student, trying to be the best possible, so most important thing is try to be good at exceptionally well in something that nobody can touch it in that thing. But outside that you may not know anything. That's the way to be. Yeah, so if you are here you are taking analysis with me, then statistics, then I kind of wonder, I don't know if statistics lecturer, but some statistics lecturers are not mathematical. No, they just say things. I mean, of course they are true, but on the contrary, you don't improve your brain. Mathematics is a way of improving the brain. So, but if you are taking abstract algebra, it does. But again, the person has to know. That's why I wanted to take a look at the picture, because certainly I don't know her, because sometimes some lecturers don't know anything. Having a PhD doesn't imply that the person knows mathematics. I mean, of course he has seen mathematics. That's why they have a PhD. So anyway, in any country it is the way, that's the way it is. I mean, it's like, I mean, you are Buddhist, no? How many people are Buddhist in this country? By birth they are Buddhist. Same thing if you take an economist, he or she may not know any economics, but he has seen almost all the words in economics. That kind of thing. Okay, so let's go through then. R star is R union minus infinity plus infinity. So you have in your mind that you know that infinity is not a real number. That's why we put it R star, and we haven't defined anything about minus infinity or plus infinity. But definition 6.2.2 says 6.2.2. I am a little bit not on over there 6.2.6 no. And before that he is saying minus plus infinity is minus infinity, and minus minus infinity is plus infinity. That is, again, it is a definition. You should not ask why. Nothing like that. If you say my name is Ramasinghe, you cannot ask how come your name is Ramasinghe? Why not Vijay Singh? That's my name. Same thing here. When you are given a definition, minus plus infinity is minus infinity by definition. Minus minus infinity is plus infinity by definition. Thus every extended real number exists a negation. Extends a negation. When he says, by the way, extended real number, any real number of minus infinity or plus infinity. That's the meaning of extended real number. So every real number has a negation, negative real number. Negative extended real number, I'm sorry. Negative x is always equal to x. From here we learn that we know for x, if x is real, negative x is x, and even for infinity that is true. For the other things you have proved it. Here is by definition. No? So sometimes there are some single names, Karuna Avati. So by name she is very kind, but by carrying character, she may be like a Devi. It's possible, okay. So ordering of extended reals, let x and y be extended real numbers, we say that x less than or equal to y. That is x less than or equal to y. This is if and only if one of the following three statements is true. X and y are, when you take x and y real numbers, they extended real numbers, they can be, both can be real. If both of them are real, x less than or y equal means what you know for real numbers. However, if by any chance, if y is infinity, x and y is infinity, when we say that x less than or equal to y, if both of them are real, you know what it means. Otherwise, y may be infinity. If y is infinity, x less than or equal to y is true. That's definition. And again, if x is negative infinity, that is also possible. Now what? See, let xy belongs to R star. Somebody says x less than or equal to y. Are extended real numbers. What you know is, if these are the three possible ways. If xy belongs to R, then x less than or equal to y. Or y is infinity. Or x. All these are O's here. X is negative infinity. If x and y are extended real numbers, and if you are told that x less than or equal to y, you know y can be plus infinity, you can be, x can be minus infinity. Or x and y are real numbers and x less than or equal to y. That's what it means. Here are some examples also. 3 less than or equal to 5, that you know. 3 less, strictly less than plus infinity, that you know. Minus infinity less than plus infinity, that is again you know. That is the only time, by the way, you have something to do with minus infinity and plus infinity. Quite often you don't have, because you cannot say minus infinity plus infinity is not defined or nothing like that. But he says 3 less than or equal to minus infinity is incorrect, he says. That is true, no, but only thing is minus infinity less than or equal to anything is true. Plus infinity greater than or equal to anything is true. That's all we do. Okay. Again, there is a proposition here. Let x, y, z be extended real numbers. Then the following statements are true. Reflexivity, x less than or equal to x. Trichotomy, x less than y, x equals y, or x greater than y is true. I suppose this is not difficult to prove. Transitivity, if x less than or equal to y and y less than or equal to z, then x less than or equal to z. Negation reverses, if x less than or equal to y, then minus y less than or equal to minus x. See exercise 6.2.1. You may need proposition 5.4.7. I don't think it is difficult to prove, and rigorous ideas are not involved in the proof. One could also introduce other operations on the extended real number system, such as addition, multiplication, etc. However, this is sometimes somewhat dangerous, as these operations will almost certainly fail to obey the familiar rules of algebra. For instance, to define addition, it seems reasonable given one's intuitive notion of infinity. To set plus infinity plus 5 is plus infinity. We say like that. In 5 plus infinity is plus infinity, we say. Plus infinity plus 3 is plus infinity. But then this term implies that plus infinity plus 5 equals plus infinity plus 3, while 5 is not equal to 3, or some student who doesn't know much, then may decide if plus infinity plus 5 is equal to plus infinity plus 3, then you subtract infinity from either side, then you get 5 is equal to 3. So things like the cancellation law begin to break down once we try to operate involving infinity. To avoid these issues, we shall simply not define any arithmetic operations on the extended real number system other than negation and order. They are the only two things we are defining. Remember that we define the notion of supremum or least upper bound of a set P of reals. This gave an extended real number sup P, which was either finite or infinite. We now extend this notion slightly. I don't know why he said that infinite. Doesn't matter, let's go. That's not that important. 6.2.6 supremum of the set extended reals. Let E be a subset of R star. Then we define the supremum of E, O is upper bound of E, by the following rule. If E is contained in R, sup is sup. Now E is a subset of R star. If E is a subset of R star, if by any chance E is a subset of R, supremum of E is what you know already of supremum of E. But if E contains plus infinity, by any chance, then sup E is plus infinity. And if E does not contain plus infinity, but does contain minus infinity, it doesn't have plus infinity, but it has minus infinity, then we set sup E to be, you get rid of minus infinity from E, then it is a subset of R, then you say supremum of E is supremum of E minus infinity, which is a subset of R and thus falls under case A, he says. We also define the infimum of E, also known as the greatest lower bound of E, by the formula inf E is defining minus sup minus E, where minus E is the set, you multiply each element by minus sign. So you have to see whether this is correct, no? Say suppose you take a set 1, 2, E is 1, 2. This is E. So actually we know inf is 1. That is from common sense. But what is his definition is different of inf. He is defining inf E by minus sup minus E. So now let's go to minus. Minus 1, minus 2. So sup of this set is minus 1. Minus supremum of minus A is plus 1, you get it. So it makes sense. That's how he is defined. Let E be the negative integers altogether with minus infinity. E is so minus 1, minus 2 all the way, including minus infinity. Then sup E is, since you have minus infinity in this set, you have to get rid of minus infinity. Then look for sup E. From our sense, it is minus 1. While inf E, actually we can say inf E must be minus infinity, but we cannot do so. We have to go to the definition. Minus sup minus E, if you take all of them minus, then you get 1, 2, 3, 4 and infinity. Then supremum is plus infinity. Then you have to put the minus sign. So minus. Example. Again he said the set 0.999 etc. has infimum 0.9. That is very clear, that's the smallest number I guess. And supremum 1. Supremum is 1, but 1 is not a member of this set. Note that in this case, the supremum does not actually belong to the set. That's true for this set also. No? If you take the open interval 1, 2, supremum is 2, is not a member of E. Infimum is 1, that's not a member of E either. He says, but it is in some sense touching it from the right. So that's kind of good language, I guess. The set 1, 2, 3, 4, 5 has infimum 1 and supremum infinity. We say, why do we say, by the way, it has supremum infinity? Infimum 1 is clear, no? 1 is the smallest one. We say supremum is infinity because it is not bounded above. That's how we define, no? If it is not bounded above, we say supremum is infinity. That's how we went. Then, let's example 6.2.10. He says, let E be the empty set. Then sup E is minus infinity and inf E is plus infinity. Somehow here sup E is smaller than inf E. First time, I guess the last time also. This is the only case in which the supremum can be less than the infimum. He is asking why. Why do we say supremum is minus infinity? Supremum is by definition the smallest upper bound. Because any number is an upper bound. So then it must be minus infinity. And inf is plus infinity because any number is a lower bound. So that is why. So this is a very special situation at which sup E is smaller than inf E, so it is kind of abstract situation. One can intuitively think of the supremum of E as follows. I guess imagine on the real line with plus infinity, somehow on the far right, and minus infinity on the far left. Imagine a piston at plus infinity moving leftward. So he has, here is plus infinity, here is minus infinity. He says, imagine imagine a piston at plus infinity. You have a piston at plus infinity. Say piston, let's say piston is something like this, for instance. Imagine a piston at plus infinity moving leftward. It's going this way. Leftward until it stopped by the presence of a set E. You have a set E, somewhere here set E. So because of this, it's moving, you have to stop because of the set E. That's the barrier. It's kind of on the way. So presence of a set E. The location where it stops is the supremum of E. That's one way of, I guess he is explaining. Similarly, if one imagines a piston at minus infinity moving rightward until it is stopped by the presence of E, the location where it stops is the infimum of E. Kind of good. Sometimes he tells stories also. That's good. The location where it stops is the infimum. In the case when E is the empty set, the pistons pass through each other. No? I mean, there is nothing to stop the movement, though supremum is landing at minus infinity and the infimum landing at plus infinity. So, for that story, piston story is good. For the other things, it doesn't play much role. The following theorem justifies the terminology, least upper bound and greatest lower bound. Let E be a subset of R star. Then the following statements are true. For every x belongs to E, we have x less than or equal to sup E and x greater than or equal to inf E. So let's say the proof of, this is an exercise, but let's prove it part A from head. So this is a subset of R star. So capital E may be having plus infinity, minus infinity, real numbers, all the things. For every x belongs to E, we have x less than or equal to sup E. This is definitely true If E is subset of R, so E is the least upper bound, no? That means it is an upper bound. So for every x belongs to E, x must be less than or equal to sub E. If by any chance it has plus infinity, then sub E is going to be plus infinity. Then x less than or equal to, again, sub E. Again, it doesn't matter for sub whether it has minus infinity, because having minus infinity does not change the sub. And similarly for the x greater than or equal to infinity. But you need to write all of them, though it is simple. You need, as I am saying again and again, learn to write. Although it is good and good to talk about torus, donuts, and all that, but to be mathematical, you have to write. You have to write. Otherwise, you won't make a mathematician. You have to write. Even if you are not good, that actually you all three are very good. Actually, you two are much better. If you cultivate the habit of writing from now onwards, you will make a very good mathematician. For some people, actually, a friend of mine, he is from Romania. So Romania had these problems, no leftist movement, and so somehow he has escaped from Romania and come to US. He was working on differential geometry. You know, I am in functional analysis now, so I am always epsilon, delta, in all these things. I am very particular at these things, otherwise you cannot do analysis. Differential geometry is like the GAN. You say, you take this one, torus and bend like that, no? You say, you cannot do it. This say, you cannot do it. So for analysis, you have to have this. For this, my friend, sometimes when I was working on Brooding's group, now I will be working with you next year. Expected to be working. That's a very difficult book, by the way. Unlike this one. I had some problem, I got stuck. I couldn't do. So I tried for 1 week or so, I still couldn't do. Then I ran into him because he is very simple, humble guy. Very simple, very nice guy. I told him, I could do it, can you show? He told me, don't try to solve this problem. If you solve it, say suppose you solve it, what will you get? Nothing. Do some research and try to solve some problem that nobody has solved. Actually, he cannot solve a single problem. Yeah. He sometimes comes and says, Rama, you don't know anything. That is true actually, I don't know anything. But you know something to the deep end. The things I do, he cannot imagine to do before his death. Yeah, to be in real analysis, you have to be very particular about every rational, every irrational, every small number. It is very important, real analysis. To him, that's how it is. Anyway, so we discussed about one, no? Yeah, then that's over. That section is over then. Let's see. 2 questions, 6.2.1, professional 6.2.5. 2.5. What is?
Reflexivity trichotomy.
You can do that, no problem. Then 6.2.11, again you can do no problem. Because I am trying to see, there are some problems sometimes you cannot do. You know, in this book sometimes, for instance, that the other day I presented
In the power.
Oh, you cannot do that. But by next year, you will be able to do that kind of things. Year after next year, you will say, oh, that's nothing, you can do that. Not now, not now. Okay, suprema and infima of sequences. Now, so far we discussed about sup and inf of sets. Now we are going to Sequence. Sequence is not a set, no. Sequence is a, things, the analysis, I know I forget when I come to this class. Because everything is very different here. It is an ordered, unending list of numbers. That's the sequence. It has an order, no end. No end. It's a list of numbers. That is my definition. That's how very recently I was writing a book for this Minister of Education. I'm writing when the books are out, good for you to read. They are very simple. You will understand, but sometimes, though it is simple, it's good for you. I mean, the knowledge you know be more confirmed when you know very little things. Alright, having defined the notion of a supremum and infimum of sets of reals, we can now also talk about the supremum and infimum of sequences. Okay, sup and infim sequences. Let an be a sequence of real numbers, then we define sup an to be the supremum of the set of elements of the sequence. That's all. No difference. Sup of the sequence is sup of the set of all elements of the sequence. So nothing new here. Infimum is the same way. Infimum to the infimum of the same set, a n greater than or equal to n. So that is an expected definition. It doesn't surprise you at all. Remember, the quantities sup a n going into empty infinity and inf are sometimes written as, or some people write like that. That's okay. Example 6.3.3. an is equal to minus 1 to the n. Thus, n going to 1 to is the sequence minus 1 plus 1 minus 1 plus 1 and so on. Then the set n going greater than or equal to 1 is just the two element set minus 1 and plus 1. Hence supremum an is 1. Similarly, infimum an is minus 1. Easy. Example 6.3.4. Let an is equal to 1 over n. Then sequence an going on to infinity is the sequence 1 over 1 actually, 1 over 2, 1 over 3 and so on. Then the set an greater than or equal to 1 is the countable set 1 over 1, 1 over 2, 1 over 3, 1 over 4 is a set. Thus sup is equal to 1, no? The biggest element is 1. Inf is equal to 0. That we have to, I guess you can prove it, no? Exercise 6.3.1. Okay. Can do. I'm sure you can do. 6.3. Anyway, here again, infimum is not a member of the sequence, or else infimum is not a member of the set of elements of the sequence. Notice here that the infimum of the sequence is not actually a member of the sequence, though it becomes very close to the sequence eventually. So it is a little inaccurate to think of the supremum and infimum as the greatest element of the sequence and the smallest element of the sequence respectively. That is true. Now let's take example, let a is equal to n. Thus a is the sequence 1, 2, 3, 4, etc. Then the set a n greater than or equal to 1 is the set of all positive integers, is a plus actually. Then supremum is equal to plus infinity because it is not bounded above. And can you see, by the way, sometimes you say supremum is infinity because infinity is there. Sometimes you say supremum is plus infinity because it is not bounded above. So you need to be a little bit careful about that. And infimum is equal to 1. That's also clear. As the last example shows, it is possible that the supremum or infimum of a sequence to be plus infinity or minus infinity. However, if a sequence is bounded say bounded by m, then all the elements a n of the sequence lie between minus m and plus m, right? If you don't understand, by the way, something when I read, you have to say. Because I am assuming that you understand. So that the set a n less than or equal to m has m as an upper bound and minus m as a lower bound. Now, if the sequence a n is bounded by capital M, then the elements are bounded below by minus m, bounded above by plus m. So, capital M is an upper bound of the set of all a n. Minus m is a lower bound of the set of all a. So, if it is bounded above, if it is non-empty, it has a soup. It has a soup. He proved no, somewhere he got stuck. And by the way, I asked you, did you go through that proof that I told you to?
Yeah, still didn't get it.
Okay, let's discuss it. I forgot to discuss. Let's do it. Now, anyway, let's go through this because this is important. Then, since the set is clearly non-empty, we can thus conclude the supremum and infimum of a bounded sequence are real numbers. Because this set is non-empty subset of R, which is bounded above, it has a sup. It is a non-empty subset of R, which is bounded below, then it has a inf. And they are real numbers, not plus infinity or minus infinity. Then he has a least upper bound property. That theorem also least upper bound property. What is it? Sometimes. Let's see. Existence of least upper bound. Theorem quite well. This is least upper bound property. Let's go through. Let a n starting from m be a sequence of real numbers, and let x be the extended real number x. So x can be plus infinity or minus infinity or a real number. X is equal to supremum a n going m to infinity. Then we have a n less than or equal to x for all n greater than or equal to m. Also, whenever m belongs to R sharp, I mean, let's see whether there is no proof and it is an exercise. Proves it. Because it is an exercise, let's see whether we can prove a less than or equal to x. X is an extended real number. Right? X is extended real number. So it can be infinity. It can be a real number also. So now we have to prove that however, x is the supremum of a n going m to infinity. In other words, x is the supremum of am plus 1, am plus 2, that's it. So we have to prove that an less than or equal to x for all n greater than or equal to m. I mean, we have to do no. So now you have to assume if x is plus infinity, you say in your proof you write x equals plus infinity or not. No, one of them no. If x is equal to plus infinity, a less than or equal to x is trivial. If x is a real number, then x is an upper bound of the set m plus 1 and so on. Therefore, a less than or equal to x again is true. Right? So I have proved that part. Then also, whenever m belongs to R star is an upper bound of 4a. Again, m can be plus infinity for a real number. He says that is a less than or equal to m for all n greater than or equal to m. We have x less than or equal to m. Again, you need to, because if m were a real number, there is nothing to prove here. Because x is the least upper bound, m is an upper bound, then m must be greater than or equal to x. So you have to consider the case of infinity also. That will not be difficult. Finally, for every extended real number y, for which y less than x, there exists at least one n Sometimes I laugh because that boy, he comes only for lunches. He's a funny guy. He's a pleasant boy, no?
Yeah.
He's not moody at all, nice guy. If there is a lunch again, I'm sure he will come. You see this one. Yeah. For every extended real number y, for every y belongs to R star, let me write this way to save time. You should not use this thing. I just write to save time. For each y belongs to R star, for every extended real number y, for which y less than x, such that y less than x, there exists at least one. There exists at least one n greater than or equal to m, for which y less than a less than x. So he is talking about this. X is the supremum of the sequence. It begins from AM. So, I mean, we discussed two things. First one is a less than or equal to x for all n. Also, if m belongs to R is an upper bound, then m greater than or equal to x. Then last one here. For each y belongs to R star, such that y less than x, there is at least one m greater than or equal to m, for which y less than a less than x. So it is kind of like my language. If you take any epsilon, then lambda minus epsilon is a small number. There must be at least one epsilon bigger than lambda minus epsilon. That sort of language here. So, of course, it is an exercise, but can we do it right now? Here, what is? I think we try the thing. X equals to 3. If x is equal to supremum, x belongs to R star by can you do it? If what it says is, if you take any number less than the supremum, any real number, I am sorry, any real number less than the supremum, there must be at least one an greater than that real number, however less than or equal to x. I mean, this side is always true, no? We have proved it actually. First part was to prove that every a less than or equal to x. Now the thing is here you have to prove, you take some number y less than x. Here is x, here is y. I made it larger, but you have to assume y is right here. Very close. No matter how close y, but less than x, there must be some a greater than y. But of course, a less than or equal to x. How can we prove it?
Y is minus infinity, the answer is trivial.
Okay.
So, when the real number y is real number, that's it.
if y is minus infinity, ANs are real numbers, no? It's a real valued sequence, no? AN, I hope so. Be a sequence of real numbers. That's how it starts. If y is minus infinity, bingo, done.
So that there exists a rational number between two real numbers. Can we?
No, it doesn't mean.
I mean, y and x are real numbers, so
So there are rationals, but AN is a particular sequence.
Answer that A is exactly in that set.
That doesn't. It's good that you give between y and x. Of course, there are rational numbers infinitely many, and there are irrational numbers infinitely many. That's very good. But here it doesn't come because we need. This is A. It is just some real number. How do we know that? Can you say it is parallel to this? This is what I have written.
Since y is less than x, y is not an upper bound of the set AN.
Since y is less than x, but you cannot assume the result that you are going to prove. What you are going to say, since y is less than x, x is the least upper bound, that kind of language you are going to use.
Okay, assume that y is an least upper bound of the set AN. I'm doing an assumption. So I'm trying to make a contradiction.
Then if you are going to take a contradiction,
Yeah.
then you have to assume the negation of the given statement. So what is it?
So, no, first of all, I'm trying to show that y is not an upper bound.
No, now you told me you are going to go by contradiction.
Yeah,
No.
yeah, I'm trying to.
You cannot mix.
Yeah,
Then you have to, if you are going to use the proof by contradiction method, you have to assume the negation of what is to be proved is true.
no, I'm trying to prove first of all that y is not an upper bound of A, the set AN. So just to prove that, I'm trying to use proof by contradiction, just to show that y is not an upper bound.
That's what we have to prove now. We have to prove that y is not an upper bound of A. And you have one A greater than y. We are proving that y is not an upper bound of the set of all A.
can we say that y is an element of the set O? It is less than infinity.
That is also true, Buddha. You are thinking of good logic man. He is thinking logical things. But what is better is that what you said to start. Assume the negation of this thing. If, of course, y is minus infinity, there is nothing to be proved. Now assume y is a real number. Then assume this statement is false. Then try to get a contradiction. Suppose y is a real number and try to get a contradiction. I mean, y cannot be plus infinity, no? I mean, y cannot be plus infinity, like how come something greater than infinity? So, y can be minus infinity, but you said then you cleared that case. Now, y is a real number and you are going to assume this thing is not true. What is then true?
Yeah.
This is not true. As for every y, let y be a real number such that y less than x. If y is equal to minus 20, you clarify it. If y is equal to infinity, it doesn't happen. It's like we are in Brahmaloka, like Buddhist people put that. Some people are in Divyaloka or Atmaloka. Luckily, we are a Catholic person. But you also go to heaven. That's after it, luckily. Okay, Patty, so let's assume this is not true. Suppose, let's say this, I cannot write, I want to say right. That's not true. Then what will you get?
X is the y belongs to extended.
No, but then now y is fixed. We have taken the y, let y belongs to r star, be such that y less than x. Then you said, if y is equal to minus infinity, done. Now, show y is a real number less than x. Now y is fixed, nothing to worry about. Now, this, what I underline part, I am assuming is not correct. So then what will I get?
For each n greater than or equal to n.
Hence, for each n greater than or equal to m,
A n is less than or equal to x.
that part is
Yeah.
always shown on
Yeah. And y is greater than or equal to a.
y greater than or equal to a.
So by definition, y must be an upper bound.
Then y must be an upper bound. Let's not say must be y is an upper bound. Now this is a contradiction. Because y is stricter than x, x is the smallest upper bound, y is the upper bound. Okay, so now you can think that homework is done. Now the reason I am doing one or two here and there, so that I want to think, I want to force you to think, logical man. Okay, now let's go. See exercise 6.3.2. Now anyway, we are almost done about it. Now, there is a corresponding proportion for infima, but with all the references to order reversed. Example, all upper bounds should be not be lower bounds, etc. The proof is exactly the same. He didn't prove it. He says proof is exactly the same. Doesn't matter. Anyway, so what he is saying is this, because here he has stated the result only for the least upper bound. He hasn't stated the result for the greatest lower bound. So I expect you write the result and prove. It's important, because I wonder why on earth he didn't write it actually, even though he didn't prove. Doesn't know to prove it. Now we give an application of these concepts of supremum and infimum. In previous section we showed that all convergent sequences are bounded. That you can prove, no? It is natural to ask whether the converse is true. What is the converse? If all convergent sequences are bounded, whether all bounded sequences are convergent. No, it is natural to ask. The answer is no. For instance, the sequence 1 minus 1, 1 minus 1 is bounded, but not Cauchy, and hence not convergent, right? However, if we make the sequence both bounded and monotone, that is increasing or decreasing, then it is true that it must converge. It's a very important result that you have to keep in mind. Let's read it twice, not once. monotone bounded sequence converge. Let An starting from M be a sequence of real numbers which has some finite upper bound. Upper bound is finite real number. M belongs to R and which is also increasing. An plus 1 greater than or equal to An for every n. Then An is convergent and in fact, which can be that straight. Let me erase this one. So you have a sequence, always good to draw graphs. You have this sequence bounded by capital M. And this is increasing. Here is 1, here is 2, here is 3, here is 4, here is some n plus 1, m plus 1, like that. This graph is increasing. 2 is little bigger, 3 is little bigger, 4 is bigger, n is somewhere here, n plus 1 is somewhere here, m is somewhere here, n plus 1 is somewhere here, always increasing. No matter how far you go, no matter how close you get to m or something, maybe m somewhere above, I don't know, I have written closer. Finally, the terms, if the sequence is An has no choice. Rather than getting almost like some number here. What is that number? That is supremum. Sup A. So if it is increasing, and it goes without saying, without the proof, that it must converge to the supremum of A. So that is a theorem and you have to write this. A is not. He says 6.3.3, that I will not prove, you can prove it. But always is very important to have the idea. If it is increasing and bounded above, I mean you cannot go past this bound. I am not saying if it is bounded above by M, this one converges to M, but it converges to the least upper bound of the set of A. So it is a natural, result. And similarly, if a sequence is decreasing and bounded below, it also converges to the greatest lower bound. Increasing sequences converges to the least upper bound. Decreasing sequences converge to the greatest lower bounds. Constant sequence converges to the constant. So now we know 3 kinds of sequences which are convergent. This book does not talk that way somehow. We want to know increasing bounded above converges, decreasing bounded below converges, constant sequence converges. So like that, we need to know what are type of sequences which are convergent. You want me to stop? You have to give some time, no? Okay, so let me see the last line is important. The sequence is said to be monotone if it is either increasing or decreasing. We see that the monotone convergence, we can only if it is. Anyway, you say monotone if it is increasing or decreasing. Monotone sequences, monotone and bounded sequences converge, you know that. Okay, let's stop and have